Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. We're recording.
There's no, the one thing I don't like about this is there's no like pew pew going on when you hit record.
Yeah.
Right. There should be something.
It's a big bummer when that happens. I agree.
Hold on. I know you love it when I do this, but I got to put my microphone right up tight.
Yeah. Let's get right up into it here.
Mm-hmm.
Chris, I've been thinking about you recently.
Yeah. Why?
You could not have said that with less enthusiasm.
Okay, let's just set the record straight. What Chris do we have today? Well, we have Chris that is mildly under the weather today.
We have a bedraggled Chris.
we do. Like, this is, oh my gosh, it started a few days ago and it just crescendoed till last night. It was at its full force.
So apologies.
We are dragging this guy out. Okay?
We have Weekend at Bernie's Chris. We have rolled him out, propped him up, and he's here for recording.
I almost cried. I'm like, oh my gosh, I am in so much pain. Just where, says Jenny, and I'm like all over the place. My skin hurts. My everything just hurt. It was not a good day. So I apologize to everybody right now for my radio voice is not up to par today.
That's true. We've got a nasally Chris, but you're going to step it up and bring the energy because we're talking about cool stuff. But before we get to that, I've been thinking about you because, well, we got a new house over here in Pennsylvania, and I have been doing some power washing because we have a little concrete, walkway. So anyway, we've been power washing. The house is old and it needed some cleaning up. And I was just thinking, I love this stuff, and I'll bet we could put together a little Chris's digging company combined with Jesse's power washing. This would be very fun.
I could be a good assistant with power washing. I love power. No, it's so satisfying. Especially when you power wash your rocks.
Oh,
it's almost like, it got scrubbed clean by a glacier and then just dropped off. And that's what the power washer essentially does. We're resetting the radiometric clock when we power wash.
It's true. It's amazing. And that's what I've been mostly power washing is we have these like stone walls around the house. It looks like a moss black rock thing, and you power wash it and the grout stands out, the reds and the yellows and the textures in the sand, they're all kind of locally derived sandstones. It's so fun to do.
What kind of power washer do you have? Is it a little electric thing?
Yeah.
Is it a gas powered thing?
No, I went and got
Jesse
the little electric one because it's enough. They make them so well these days, and you don't have to deal with.
True.
I mean, it's like true. I forget what it is, 2,300 psi or something like that. I mean,
that's enough.
It does enough for what I need to do for the most part.
It'll peel the paint off a car.
Yeah, that's right. And
I found that out the hard way once.
I don't want to be doing that. So it's good. I don't have a 4,000 psi thing. I'd break stuff with that. So anyway,
all right.
Yeah.
All right.
Okay, you
Good
can be my
stuff.
assistant. I'll assist with Chris's tractor company. And
I'll give you the shovel. You do all the hard work, and then I just come along with the tractor and get all the glory.
There you go. Perfect. Love it. And I can do the same with the power washer. You can
I'll be your power washing sidekick.
Yeah,
you
can kind of scrub it a little bit, and then I'll come by power wash it. Take all the glory. Sounds great. Okay, cool.
Love
it.
Scrub it a little bit. Okay. All right. I don't know about that.
Give you a little wire brush. Take the stuff off. That'd be good. So if you need some rocks cleaned, Chris and Jesse will come. We'll bring the power washer. We'll clean up your rocks for you.
If you have rocks at your home or rocks at your place and you don't have a power washer, that's a problem that needs to get fixed.
Yeah.
You got to bring the life back out.
Especially, Chris, if you have rocks with garnet eyes in them, because that's our topic today. What's your experience with these things? I mean, this was your idea. Garnet eyes. Like, hey, this is a cool thing, cool phenomenon. Let's talk about it.
Yeah, I think these are amazing. When you go for a hike in Death Canyon up in the Tetons and you just come across these outcrops and you can't miss it. I don't care how old you are, what your level of geoscience expertise is. You look at this and you're like, oh my gosh, it looks like thousands upon thousands of eyeballs just staring right at you in this beautiful dark colored rock. It's amazing. And then you and I have experiences in upstate New York with the Gore Mountain garnets and
the Gore Mountain garnets. I think this is the origin of the idea. It was, I forget what we were talking about, something, and I mentioned Gore Mountain, and you're like, oh, we got to do an episode on the garnet eyes in Gore Mountain. I mean, they are spectacular. So what we're describing here, what we're talking about is we're going to talk about a large class of features that are, I don't know, they're called reaction rims, they're called depletion halos. They're called all sorts of,
Which
they're
are two
called,
different things, by the way.
yeah,
Yes.
a couple different things. But the point is, we see a bunch of these types of things. They're basically a certain mineral. They're usually found in metamorphic rocks. One mineral that is rimmed by another one. And the one you're referring to is a garnet eye, what are called garnet eyes, because there's a garnet and then it's rimmed by plagioclase, right? It's like a really white plagioclase. Is that right?
A really white plagioclase that's in an overall very dark colored schistose rock.
I think, Chris, maybe we're going to talk about the broad category of stuff, but kind of center it around this sort of garnet eyes phenomenon. But I just want to get a couple definitions here. Yeah, sorry, go ahead.
Hold on. Before we do that, Jesse, we always try to center things around, well, why is this important? Why do people need to know about garnet eyes? And here's our take. We were just talking about this, and it comes down to really two things. One is they're just really cool. I mean,
Yeah,
enough said.
They're beautiful.
You know,
Yep.
they really are. You need to go get yourself some garnet eyes. Okay?
Oh, yeah.
You need to do that if you're into rock collecting and things like that. But the other thing is, though, from a scientific standpoint, they're really important because this kind of metamorphism that we're talking about, it tells us a history of the rock. It gives us this kind of geochemistry / history. What did this rock get subjected to?
And there are great depths that we could go to in the weeds about various chemical reactions going on, but it all comes down to the sort of chemical reactions that are occurring in the rock. And a couple quick definitions to kind of set the stage here. First of all, we're talking about minerals that are metamorphic, and they're usually, Chris, in the example you gave, like the garnets, they're much bigger than the other minerals in the rock, like the background minerals so much in the rock. And we call those porphyroblasts or porphyroblasts, depending on which side of the Atlantic you're on. But these are...
Oh my gosh, are you serious? You're really... No.
I knew I'd get a reaction out of that one.
Are you serious? What did you just say?
Porphyroblasts, if you're in the UK,
gosh.
if you're in the English system, maybe?
No.
Porphyroblasts.
I'm sorry. It's porphyroblasts.
We'll stick with porphyroblasts. These are metamorphic minerals that are growing as the rock is heated up and put under pressure. These garnets, in this instance, are growing, and they're actively growing or they're actively breaking down, but they are metamorphic mineral. They're not there in the rock initially.
The inside of my head this weekend became a gigantic porphyroblast. I mean, it just depleted everything else around.
You got metamorphosed this weekend, huh?
I did. I tortured. We've always talked about metamorphic rocks as being tortured rocks, and my head was enlarged
and put under a great deal of heat and torture. Okay. Yeah.
It was.
So these things, Chris, the ones we saw at the Gore Mountain mine, I mean, these are unbelievably big. These things are softball or volleyball size garnets. I mean, they are enormous and beautiful, and they often have thick rims of amphibole around them. So black amphibole or biotite around, like rimming them. And that's a different mineral, right? Like you just described a black rock that has in the Tetons that has garnet rimmed by plagioclase. And I just described one in upstate New York that has garnet rimmed by amphibole. Two very different reactions that are going on here in two different categories of these reaction rims or depletion halos or garnet eyes. There are a bunch of different categories of this. So the history is kind of the important part, and there's different ways to form this, but they're all about metamorphism and mineral reactions occurring.
And sometimes, again, depending upon your previous exposure to this kind of stuff, you might see or have this referred to as Augean gneiss, something like that.
Yes,
okay?
That's right.
And
I want to come back to that, Chris, at the end. I want to kind of touch on this again because the Augean or Augen, depending on how you want to pronounce it, that word is the German word for eye. So I've seen up in the Northwest Territories, a lot of the gneisses that I walk across are actually, we would call them Augen gneisses because they have these little eyes in them, and they can be really small eyes, they can be bigger eyes, but they have this kind of eye-shaped feature to them, which means that they've been metamorphosed. Chris, do the Tetons ones, the garnet eyes, are the plagioclase rims perfectly circular, or are they a little bit like eye shaped and squished out on the edges?
Yeah, they're eyeball shaped. So there's been some shearing involved in this as well. Not just heat, not just pressure, but the same kind of forces that cause foliation in metamorphic rocks was a directional pressure. Yeah.
And this is a kind of a key point that you should think about if you're listening to this. Like, okay, the garnets are often very circular, almost always circular, at least if it's a single garnet grain. And then the plagioclase is kind of the eye shape, the white of your eyes around it. There's a reason they're called it. It's kind of like a pupil, circular pupil with an eye shape around it.
So Jesse, sorry to interrupt you, but what you're saying is that in this instance, the white around the garnets is deformed, but the garnet is not. And so just think about that a second. What does that mean? Why would certain minerals be deformed and look like they've been stretched and tortured, and then in the center of it, untouched? So Jesse, why don't you
It's a good
enlighten us?
question. I want to give the listener time to think about that. Garnet is one of the few minerals that will not deform. It is just such a solid crystal structure that it's really, really nearly impossible for garnet to actually deform under these types of conditions. So the plagioclase is being actively deformed and growing and getting squished, and the garnet is not getting squished. It remains this kind of softball or this round ball shape. So that's a really important reason. And part of the reason, Chris, I think they look so beautiful, like if the entire grain, if all the grains were squished, I don't know, it wouldn't be as striking to me, that eye shape. It's really a round pupil with a sort of a curved and squished out eye shape to it.
That's right. So the Tetons have definitely the eyeball shape. You can see the shearing that happened in this kind of like directional force. But the Gore Mountain garnets, Jesse, they did not.
They did not.
That's just you have a black rim around these beautiful garnets the size of a baby's head. Like they're just amazing.
It's amazing.
Oh my gosh.
I love the way you phrased the two differences there and highlighted the two differences, because this is going to give us a really good way to talk about the different ways to form these reaction rims or reaction halos or these eyes. There's two fundamentally different ways. Which one should we talk about first?
Well, I think let me take one that makes like the most sense to me, and I'll leave you with the other one because they're very close, but they're distinct processes that are going on. They're very different. And so we just need to tease that out a little bit. So, like you said, there are two ways or two categories of these metamorphic eyes or these porphyroblast eyes that you get. The first one is where you have minerals, new minerals that grow in the rock. And basically, what are you doing to the rock? You're cranking up the temperature, you're cranking up the pressure, and that can destabilize the minerals that are already in the country rock, the minerals that were already there. And so if the temperatures and pressures are right, let's say, for instance, to form garnets, then the garnets are just going to bleed those elements out of the host minerals, and they're going to grow right inside of the rock. And these are porphyroblasts that you get here are just some of my favorite things in the world. I mean, I have this garnet schist from Wrangell, Alaska, where these garnets they're just enormous, but they grew right literally inside of the rock. And you can clearly see that because the minerals are kind of like stretched and elongated around the mineral. So basically what's happening is these minerals are just taking what they want because those minerals are stable under the new conditions, the metamorphic conditions.
And these reactions get really, really complicated, and there's many different forms of the reaction depending upon the composition of the rock. And we've kind of talked about the complexity here when you start thinking about the chemistry of a rock. But the Gore Mountain garnets that we talked about, in the simplest sense, that's the version of this number one. The garnet was growing, and one overly simplistic way to think about it is garnet and plagioclase are kind of two ends of the reaction. So garnet is consuming plagioclase, depleting the rock around the garnet that's growing from plagioclase because it's kind of soaking up. The plagioclase is breaking down, it's diffusing towards the garnet, and it's forming garnet. That's an oversimplification, but we can think of it that way. Like it's a depletion halo around the garnet as it's growing. It's consuming all the other stuff around there. And the other stuff's reacting out because the garnet's growing and taking it all in. So I like the way you phrase that. It just takes what it wants. The garnet's taking what it wants and leaving behind what it doesn't want.
Yeah, so basically you're getting new minerals on both sides. You're getting new minerals that are the porphyroblast, the things that we're focusing on, but also the minerals that form the ring around it. In the case of the Gore Mountain garnets, these very dark rims around it, those are new minerals too. They didn't exist in the rock before the metamorphism happened.
So you get this reaction rim that's kind of, you're seeing what the garnet wants and what the garnet doesn't want, I guess. Or you're not seeing what the garnet wants and you are seeing what the garnet didn't want, if you can put it that way. So that's one category. And that's, I think you're right. That's a simpler one to kind of understand. These are what we call depletion halos. The new minerals are growing, depleting the rocks around them. The other one, number two, the different way, and it's a nuanced difference. It's really very similar process, but there's a kind of a big difference, is that the other way is more of a one-to-one reaction. You have reactants on one side and a product on the other. So you're taking the classic example that I've seen is as garnet breaks down, it breaks down into chlorite and quartz. And so what I've seen in these old metamorphosed rocks that had garnet in them is as that rock was metamorphosed into the garnet stability field sometime a long time ago. And then at a later time, it was metamorphosed again, but at lower temperature. And the garnet then breaks down. And then the product of that is chlorite and quartz. And so you get this beautiful chlorite and quartz rim around a garnet, and you can see the garnet's kind of being eaten up. It is the one that's being eaten up. So it's garnet going to chlorite and quartz. It's just a one-to-one reaction. And these get massively complicated. Like there's so many different ways to form these one-to-one reactions.
So question for you then. I think of this, I want you to see if this is a proper way of thinking about it. I think of the process you're describing is an inside out kind of reaction where you have the garnets that were formed earlier, and then it's subjected to new conditions, new temperatures, new pressures, and now they're going to bleed out into the surrounding minerals and form chlorite and quartz in this case, right? So the process I described is an outside in process, and this is an inside out process. Is that adequate? Does that work?
Yeah, I think that's right. Inside out is a little hard for me to picture in a way, but I kind of think of it as like, okay, if you have a basketball, brand new basketball, indoor basketball, it's, beautiful leather, and you take it and you use it outside for a while. The outside's going to get really sort of scuffed up and beaten up. And that's kind of what's happening to the garnet. The garnet's breaking down. The reaction's kind of progressing inside as the garnet is breaking down, or better, maybe an ice cube in water is a better example. Put the ice cube in water and it melts from the outside in. It's reacting out as it's warming up because it's destabilizing.
Okay. Let me give it another crack then. Okay. We have, in previous episodes, we've spoken a lot about Bowen's reaction series. And in Bowen's reaction series, as you take these early formed minerals like olivine and calcium-rich plagioclase, and you allow them to cool down in a melt, these crystals are suspended in magma, let's say, you lower the temperatures, and the olivine and plagioclase will react with the melt and begin to turn into different minerals. Well, you can create the same thing that you're describing, these kind of reaction rims where just the surface of the mineral is reacting with what's around it, not all the way through.
That's exactly right. And then it kind of freezes in place. So in the instance of this garnet goes to chlorite plus quartz, you need garnet plus water, and then you can react to chlorite plus quartz. And so you don't react all the way because you don't have enough water in the rock to do that reaction. So that's just like one instance of this. So the reaction's kind of frozen partway through. And so, Chris, there's tons of examples of this. You can have pyroxene that's rimmed by garnet and plagioclase. You can have garnet that's rimmed by plagioclase and orthopyroxene. There's a crazy, really high temperature metamorphic ones where you have like sapphirine, which is kind of turquoise, rimmed by orthopyroxene, then seliminite around it. So you can have these really massively complicated reactions that you kind of get preserved in different rings, kind of growth rings around this porphyroblast.
If you're listening to this and you want to go down a rabbit hole, then start looking at the chemical formulas for some of these minerals that you just described, right? If you look at these chemical formulas, which are really complicated chemical formulas, you can start to see what's happening. Is the porphyroblast taking what it wants to form that new mineral and then leaving behind other ones. You can start to piece this together, but we can't really do that in a podcast because it's we need visuals for that.
Yeah. Chris, that is such a great point. This is an amazing rabbit hole to go down, to go on the Google train and start looking at these reactions. It'll teach you a ton about metamorphic petrology and geochemistry. This is, you kind of touched on it at the end there. This is the story that these rocks tell. We can tell so much about what that rock experienced based on these reaction rims. And so the garnet eyes, back to the Tetons, the garnet rimmed by plagioclase. This is an example of the number 2 version. The garnet is reacting out to form the plagioclase. There's debate about how these form, and in different rocks they form
Of
different
course
ways.
there is.
Of course
You guys,
there is, right?
yeah, of course there's debate in this.
But different rocks have different histories that end up with the same result, this garnet rimmed by plagioclase. One of the coolest ones, I think, is when garnet's a higher pressure mineral. So garnet's happy at higher pressure. It's less happy at low pressure. And plagioclase is very happy at low pressure. And so in a very oversimplified way to think about it, you take a rock that has garnet in it, the garnet's sitting there very happy, it's high pressure, it's deep in the crust, and you lift that out of the crust. You start to like thin the crust, or the mountain range kind of collapses out and sloughs out to the side, and rocks come up, and we have this isostatic rebound. The rock gets brought to the surface. That garnet can react to plagioclase and sort of start to react out, and you get these plagioclase rims. That's kind of one model. I mean, to look at that garnet rimmed by plagioclase, say, oh, I can tell that that rock went from deep to shallow, and that's the result of it. This garnet as a result of that is so cool. That is just a really cool story.
Jesse, I want to double click on this a minute because, you know, we did a whole audio book and we've done podcast episodes on the Grand Canyon. So how do we know the depths that the Vishnu schist was exposed to? I mean, Jesse, we're talking about ridiculous depths, in excess of 12 miles deep. How do we know this? The garnet tells the story. Like you said, these garnets form in really, really high pressures. And so it gives us this nice bracket of temperatures and pressures, which equate to depth. So yeah, I just wanted to double click on that this is something that we've talked about before, just maybe not with this nuance to it.
No, I agree, Chris. And I think there's one metamorphic petrology. This is certainly firmly in the category of metamorphic petrology. It's such a cool field because you tell great stories with metamorphic petrology. Like, I mean, rocks moving around in the crust and getting heated up and cooled down and put under intense pressure. I mean, the stories you can tell with metamorphic rocks, it's pretty cool.
You know, Jesse, I was thinking about this actually today, is that I think that we have a clearer understanding of how metamorphic rocks form than we do igneous rocks, intrusive igneous rocks.
I agree, in large part because of these reactions. The reactions are so crazy and cool, and there's so many different components. Like an igneous rock, there's not that many reactions that happen in it because it's a magma. Like it's not like a sediment. The sediments get wild and crazy. I agree. They tell a more vibrant or colorful story of how the earth has worked, I think, in metamorphic rocks. So that's certainly true. I have a question for you, Chris, to maybe end on here. I think, and I struggle with this myself too, so it's not just students, but my perception is that students, when we talk about metamorphic reactions and we talk about the story that metamorphic rocks tell, we often kind of work from low temperature to high temperature. So we go from biotite up to staurolite and then to garnet, and we eventually end up at the high temperature stuff, and we end up at eclogite, and okay. We often forget that these reactions happen on the way down too. So like the reaction of garnet going to chlorite plus quartz is what we call a retrograde reaction. It's a rock going from higher temperature back to lower temperature. And I'm wondering what you think about this. Is this something that people struggle with to even think of as important? And if they do, is it a big deal?
Here's my thought on this. Here's my take on it. You know, we have talked about some really important metamorphic rocks. We've talked about eclogite and blue schist, but what gets focused upon in any intro level geology class, those don't get mentioned, but those tell us the most information. Right? They tell us what happened. They tell us what was the tectonic setting. But instead, we focus on slate, phyllite, schist, gneiss, things like that, right? So I do think it's important. I just don't know why I think they're not given their due. Why do you think that is?
Well, it's tough. I wish everybody would learn this in an intro class because it's just so cool and so important, and just shows, I think, how deep the fields of petrology are, like how well we can work out the history of a rock. It's really impressive how well we can do that. But I do think it's pretty deep. Like, you got to have a pretty solid geochemistry, mineralogy background to kind of get to that story. So there's like a reason that metamorphic petrology is taught in like third or fourth year of college, because
Yeah,
you
I
kind of
don't know about
got to
that though,
build to that.
Jesse.
No,
I
you
think
don't.
no, I think anything can be simplified. Anything can be boiled down to here's what's important about this. This is why this should be covered in an intro level class. You can distill it enough that why is eclogite an important rock?
Yeah, that's true. That's true.
And we don't have to get into a lot of the specific. We don't have to do that.
You're right. I'm okay. We're doing it this semester. I just started teaching. I just did minerals this week. We're teaching it. We're getting into garnet eyes by the end of the semester.
There we go. There we go. Absolutely.
Yeah.
Yeah. So before we end this, Jesse, I just want to encourage our listeners to Google image some of these things. Look at the garnet eyes in the Tetons. Look up the Gore Mountain garnets. Look up Augen gneiss or Augen gneiss. Look up garnet eyes and just allow yourself to go down a little bit of that path. It's just, these are shockingly beautiful rocks.
So beautiful. So beautiful, and tell a very colorful and vibrant story of the rock itself. So with that, Chris, I think that's a wrap. If you want to support us, there's two ways to do that. First, go to our website, planetgeocast.com. There's a support us link there. We just revamped the website a little bit. Looks quite good. And we've got some more stuff coming to the website pretty soon, so stay tuned to that. You can also download our mobile app. That's the Camp Geo mobile app. First link in your show notes. There we have a range of audiobooks for sale, including a bunch of free content, which is effectively the intro class that Chris and I teach in audio textbook form, with a whole bunch of custom-made images to really drive home the point. Geology is such a visual science. We feel like you really need that. You can follow us on all the social medias. We're at Planet Geocast, and send us an email, planetgeocast@gmail.com.
Cheers.
Peace.